All right, thanks for sticking with us at the end of the day. There you go. All right. So this talk is for obviously a certain subset of people. If you don't know what the acronyms at the top of the slide mean, I would say just go get a beer now. Or if you've ever been interested in reconstructing evolution and ancestral geographic ranges in a way that forces you to look at the world through lenses that make continents look like that, or islands look like that. So it's this common issue in historical biogeography. If you have a phylogeny and you want to reconstruct the evolution of geographic range in this very simplistic way, the question is, what model should you use? And so Nick obviously touched on this at the end of this talk. So it's worthwhile, I think, to just consider really what models are. Like, what models, what's the purpose of an evolutionary model of phylogenetic tree? Well, in just very general terms, what we want to do is explain the data at the tips of the tree with reference to stochastic events, right, in which the probabilities of those events, the P, is some function of rate and time, right? So typically what we're doing is we're integrating over time these transition rates to get these probabilities of ancestors and descendants, and that allows us to calculate the likelihood. Okay? And the point I want to emphasize right here is that time, I think we would all agree, is sort of this fundamental axis of evolutionary models, right? So the extent to which an evolutionary model gives you inferences or answers that have no dependence on time or make no reference to time, I mean, you can judge for yourself how useful that is, okay? All right, so with reference to DEC and DEC+J, this is a choice that people face and have faced a lot in recent literature since Nick published his paper of whether to use DEC or DEC+J or some other variant of DEC in Biogeography. So just in a nutshell, so what's DEC+J? Well, it's DEC, it's vanilla DEC plus what let's just call jump dispersal, right? So jump dispersal is this idea that like a single propagule can travel a great distance to an area, establish a new lineage, and that speciation event, caused by the dispersal event, accounts for what you would call an internal phylogenetic node on a tree of interest, right? And so that's DEC+J. It gives you this parameter, this free parameter J, that basically is a dial, right, that lets you adjust, maximize the likelihood by how much these jump dispersal events happen at internal nodes relative to other kinds of events. And so the promise here is that, we have this different model. It has a different parameter. We can use model selection to compare these likelihoods. So Isabel, Sanmartín, my co-author in this talk, and I we're editors of the journal Biogeography, so we've noticed this trend, right? And I think it's probably apparent to many people in other journals. But there's this great increase in the use of DEC+J in the literature. But what's kind of interesting is that relatively few papers are actually interested in jump dispersal as a process, right? So they're not directly testing jump dispersal, any hypothesis for the jump dispersal. They're just doing this model selection between DEC and DEC+J for some other reason, right? Because they want to be objective, because the reviewer asked them to do it, and so on. And so, to us, this is kind of distressing, right? Because it's pretty clear to us that, so here's the take-home messages, so you might want this to be exactly this slide. So DEC, is not a very good model of jump dispersal as an evolutionary process. The one I want to sort of emphasize here is that the likelihoods are not statistically comparable. Like, to do model selection on these models is not actually valid. Okay, so let me explain why. So remember, what we're trying to do is explain the data at the tips, these geographic ranges, let's say 2 areas A and B, through stochastic events along a phylogeny. Now, DEC and DEC+J, all DEC sort of based models, are unusual in the sense that there's not one single process, right, that is explaining the data. There's actually 2 processes. One is anagenetic, the A, and one that is cladogenetic, the C. And these are very distinct processes, as will become very clear. And in a way, you can think of the fact that there are these two sort of competing processes explaining the data as a flaw, right? Because, well, they're very distinct, and as we'll see, it's not sort of a level playing field when it comes to explaining the data. Okay, so cladogenic events in this context are kind of like hazardous. So just to go into more detail, so these the anagenetic process is very well understood. It's just a continuous time archive chain of discrete events of dispersal of range expansion, range contraction, in which the probabilities of events are time dependent. It's all very well behaved statistically. Okay? And you can think of it this way: so the probability of any anagenetic event along the branch of the tree is the product of two probabilities. The probability of the event occurring in time, and the probability of the outcome of that event, right? So you multiply two numbers, it's two numbers less than one, you're going to get a smaller number. So by contrast, cladogenetic events in DEC and DEC+J are these range inheritance scenarios, right, where there can be different outcomes depending on what the ancestral range is. DEC is based on this idea that the ancestral range is basically subdivided or just sort of passively fragmented, whereas in DEC+J, obviously, you have, here's the coconut jumping from one island to the next, okay? And so, so DEC+J basically just expands the scope of what can happen cladogenetically at these internal nodes of phylogeny. Now, this is a bit of a problem because these cladogenic events are clearly not time dependent. They're restricted to be occurring only at the internal nodes of the fixed phylogeny, right? So the phylogeny is not seen as some outcome of a stochastic birth-death process. It's just sort of fixed. And these cladogenic events are just fixed, okay? So the probabilities associated with these events are just the probabilities of what the outcome is, right? We're not taking into account the probability of the event in time. So jump dispersal as a process is not modeled in DEC+J as a time-dependent process. Okay? So that's basically the reason why, we would say that it's not a good model for the process. It doesn't take into account, for example, the jump dispersal events that might have occurred along branches, for example, but didn't because of extinction and so on. Okay. All right. So what we have is a situation where we have two processes. So the likelihood is the data given these two processes, probabilities of these two kinds of events. And because anagenetic events are multiplying two small numbers, cladogenic events is just one, probability of cladogenic events is very large relative to anagenic events. So the contribution of these cladogenic events is very large to the likelihood. And to understand this intuitively, imagine instead of explaining the data, you're trying to buy a car, you have to carry the cash to the dealership. You want to carry it in bills or points, right? So these are cladogenic events versus anagenic events. And so what happens in both DEC and DEC+J, but much more so in DEC+J, is that you can get situations where the anagenetic, well-behaved probabilistic continuous time archive chain portion of the model just disappears entirely. And you explain all of your data just by cladogenic events. Okay? And so consider just this kind of like, kind of trivial example of one sister pair of disjunct species and then a couple of outgroups in area B. Now both DEC and DEC+J can actually explain these data without any anagenetic events at all. All the change happens at the nodes. Okay? And in fact, that's and so in DEC, there's basically one scenario of ancestral, one ancestral sequence of scenarios in which that requires no anagenetic chain. In DEC+J, it adds 4 more, right? And you might think, well, it's not time dependent, it's no big deal. You just sort of recover what's the most parsimonious solution or something like that. And this actually, in this particular case, that's not true. Like, you don't recover what you might consider to be the most parsimonious solution. If you maximize the likelihood of this scenario in DEC+J, you crank the dial for j all the way over, maximize j, which means that you exclude any phylogenetic scenario that doesn't involve jump dispersal. So you end up inferring these two sequences, both of which involve jump dispersal at every node. Okay, so this is one kind of consequence of not being dependent on time that one should be aware of. Okay, so to get to the crux of the issue, though, like, why aren't they comparable? Why aren't the likelihoods comparable? Okay, so model selection typically assumes that the models that you're comparing, the processes differ in their probability parameterization, right? The number of parameters or how the parameters are assigned to probability distributions. So that, you can think of it as the probability distributions are governing the probabilities of events in which the events are otherwise equivalent, right? That there's, for example, that there's just antigenic change. That's not the case of DEC and DEC+J. DEC is DEC+J. The antigenetic part, this continuous time part, is the same. And the only thing that's different is the relative explanatory power given to these antigenic and phylogenetic components. Okay? And as I said, these are not equivalent, and they differ in terms of their sort of intrinsic magnitudes. So visually, with the, to get a better idea of what I mean, so this is typically what model selection is assuming. So here, this landscape, explaining the data, it means walking from start to end, right? And the model is defining the hilliness of the landscape and defining like how circuitous a route you need to take to get from start to end, right? And so this is a case in which these probabilities are defining the landscape. But importantly, it's assuming that you're taking steps along the way, right? And both models are taking steps along the way. DEC and DEC+J, the landscape is the same. Okay, example is exactly the same. The only thing that's different is that you've introduced these teleportation points along the way, where you enter on one side, you can instantly zap to anywhere on the other side that is optimal, right? And the difference is that DEC+J sort of gives you a bigger radius of those teleportation points, right? It gives you an expanded scope of phylogenetic change where you just instantly change. You don't have to account for time, basically. So, and in extreme cases like shown here, you can actually just traverse the entire landscape without having to take any steps over. Okay, so that's basically, that's basically my argument. So, if not DEC+J, so Nick already touched on this, classy is obviously, I think, the thing to do, because it phylogenetic events and antigenic events are sort of unified in a temporal dimension. What if you're not interested in diversification or jump dispersal? If you just want to infer ancestor ranges on a tree, I would say then use a DEC-based model, but don't use model selection. Just choose what seems reasonable based on the system, the data, and final point, just appreciate, that ultimately these phylogenetic events that the model is giving you are not dependent on time, and so, just have to be cognizant of the fact that any inferences that you make about these phylogenetic events are made in a context where time doesn't matter, and so it should just, my recommendation is should just give you pause. If you find yourself basing a lot of your impact of your study on these phylogenetic events, I would say proceed with caution. Okay. Right.
So that's interesting. Right? So, but just want to see if I understand your point clearly. So, the DEC model is describing a process that's happening on an existing tree, right? How the geographic range changes over the tree and nodes. The DEC plus jump model is not just a model of something that's happening along a tree, it's something that's giving rise to the tree, right? If a dispersal event causes a speciation event, then now this is a process that's actually changing the tree, potentially.
you could model it, arguably that's the way to model it as a birth-to-death process, but that's not what DEC+J is doing.
Right, but that's essentially what.
That's another way of framing the problem.
Right, so I would put it another way. I'd say that a jump dispersal model would have to do that, right? It'd have to be a process that describes the.
Well, obviously it doesn't have to, right? Because DEC+J exists, right?
Well, for it to be a coherent model.
Well, I think, right. I think, in general, like, statistics is a lot more subjective than people, I think, often appreciate. Like, models obviously are constructed by, humans with subjective kind of, so judging whether a model is coherent or whatever, I don't know. I don't really know what that means, actually, coherent. But, so is it a good model or bad? Ultimately, to me, it's a matter of opinion.
So I don't mean whether or not a model is a reasonable description of nature.
Okay.
By coherence, I mean, can you simulate the process that's giving rise to the tree with geographic ranges at the tips? And so,
so Nick has done a lot of simulations, and but I think one thing he hasn't done, and maybe you can correct me if I'm wrong, Nick, but the simulations that so far have been done have not treated jumps as a time-dependent process. Is that true?
No, they did. There was the big set of simulations in Matsui 2014. It was a birth-death process, and all you got to decide is, do those birth events, do they only include vicariance and sympatry, or do they include vicariance, sympatry, and jump dispersal? Right, but what you did, there wasn't a rate of jump dispersal. Right? So the rate is
simulation in which there was a parameter that said, there's this instantaneous probability of jump dispersal relative to something.
In the simulation, the rate is just what's the rate of speciation times per speciation event, what are the relative probabilities of the different kinds of phylogenetic events.
Right. So jump dispersal is not time dependent.
It's time dependent because the speciation rate is time dependent. So that's why when you add the Yule likelihood for the tree to DEC or to DEC+J, both of them come out as equivalent to Lattice likelihoods. So if you want time dependence, you multiply by the Yule likelihood, and you're set. Now, it's completely valid to say distinction is a real process, and the Yule likelihood is a poor model, right? Because it's pure birth. That's totally valid. It applies to both models, and it applies to a lot of other methods that we've got. But yeah.
So if this were a generative model, right?
Yeah.
There could be jump dispersal events that would happen at any time over the course of the history of the tree.
Yes.
And because it's a birth-death process, some of those speciation events would give rise to changes that we don't see.
If extinction is above 0, yes. But if you assume extinction is 0, which is what the assumption is.
But the E in DEC is extinction.
It's range contraction. It's not really the same thing. Range contraction to 0 would be
its extirpation
process, and that's it's a range contraction process. So to get the likelihoods to agree, you do have to pretend that the null range and state can keep existing, right? But that whole null range thing is quite peculiar, and I copied it from the DEC model, right?
So you can simulate a process that gives rise to a tree with ranges, where part of that process is speciation events that happen because of this.
Sure. Yeah. Yeah. It's all. I feel like people get confused because you can either multiply the speciation rate by the fractional probability of the different kinds of speciation events, or you could do it. Or you can have an individual rate for each kind of phylogenetic event by itself. It's the same difference.
So there is an instantaneous rate of jump dispersal.
Yeah, there is.
If you add the Yule likelihood, then there is. And everyone can go see the script on the page, convert to class if they want, and run it like it's right there. So.
I mean, if there is an instantaneous rate of jump dispersal, then it is a probabilistic model. If there isn't one, then it isn't.
See,
it's
framing
a probabilistic model.
Actually, that's what. So DEC+J is probabilistic, right? So this measures. Actually, I should correct. So actually, as if one Biogeography, it's not strictly probabilistic, but then you can ask Michael Lenz about this. It's easy to make it fully probabilistic. Probabilistic doesn't mean that much, right? Because you can have probabilities that are not related to time, right? As I was, I mean, that's kind of the point of my whole talk. So, like, being it probabilistic in itself doesn't mean much. The question is, do the probabilities sort of make sense with respect to evolutionary time? And the answer, with cladogenetic events and DEC+J, the answer is no. And to my mind, that's like kind of a problem. And it's worse than DEC+J. That's basically the